We can this thing. So, hello everyone, and welcome. Good evening, good afternoon, good morning to all of you who could join us today. Uh, we're meeting at a rather terrible time in India, as you know, and I think many of us have been very stressed about the situation, the well-being of our family members, friends, and there have been tragedies everywhere. It's a kind of a really unfortunate period we are going through, but I thought that we should nevertheless free ourselves, or rather not be chained to this depressing situation that's unfolding around us, but perhaps take our mind for a little while at least to something more eternal and more which will live long past all of us. So this is why we have today's Big Questions series, and it's a great pleasure to welcome Professor Subir Sachdev from Harvard to this episode. As you know, we started this last year during the lockdown, and this is with Subir, we'll be sort of completing the first year of this, and we have really ventured into many different domains, starting from cosmology, the very big, and so on, and also the very small, the particle physics with Nima, then into the world of the mind with Surya, and last time into the mathematical universe with Manjul. And today it's another very fascinating universe that Subir will take us into, which is the quantum universe. Let me just share my slides. 1 minute. I just have a little bit of this thing. Where is it? Okay, yeah. So, okay, so Subir is so we'll really have a session, and Subir will hopefully disentangle quantum mechanics for us by entangling us into it. But Subir is the Herschel Smith Professor of Physics at Harvard. He's really a pioneering physicist, and has numerous recognitions, and I just wanted to pick out the Dirac Medal, which cites his pioneering contributions to many areas of theoretical condensed matter physics, and then goes on to list the really impressive list of contributions. The Lars Onsager Prize of the American Physical Society, is the Fellow of the National Academy of Sciences, and so on. And it goes on. He has again been a pillar of support for ICTS through by being part of our international advisory board for a very long time, has been helping us in as we grow our faculty in different areas, especially in condensed matter physics. Subir's work has been pioneering. It's very, I think, amongst contemporary theoretical physicists, it's very unusual to have someone like Subir, because in an era of specialization where people sort of find their niche and sort of focus on that, Subir has enormous breadth, and this has we have seen this repeatedly. In some ways, he has brought ideas from string theory, from the physics of black holes, to bear on questions in strongly interacting systems, strongly interacting materials, and I'm sure you'll hear about that from him today. But he has also gone, the flow has gone the other way. So one of the models which is currently very influential in string theory for understanding the physics of black holes and features like quantum chaos and so on, is a model proposed by Subir Sachdev model, which has been a very important model in that it is solvable, and you're able to actually see many features which are otherwise normally, which would be out of reach to a sort of analytical understanding. So this has influenced things, of course, in condensed matter physics, but as I said, the ideas have flown the other way. So it's very unique to have someone who's sort of taken ideas from string theory to a subject at first very far removed like condensed matter physics, and vice versa, helped in the flow in the other direction as well. So this is part of the reason why I think Subir is, and at the heart of a lot of this is the phenomenon of quantum entanglement, which he will take us through today. But before I hand over to Subir, I just want to mention, of course, ICTS fundraising. Thanks to all who could contribute to our annual fundraising, and you can continue to help as we build our ICTS endowment. And a very important way in which you can help our efforts, especially now with this lockdown, is to connect connect me with potential supporters and well-wishers anywhere across the world, and of course spread the word amongst your circles for people who might want to be engaged with ICTS. So thank you again for all your support and for showing up at such a critical moment, but I hope you will find it nevertheless exhilarating. So the pilot, onto the pilot, Subir, for the journey. Yeah. Let me stop my share. Yeah.
Okay, I hope you can all hear me and see my screen and see the yellow green circle. Is that all right, Rajesh?
Yes, yes.
Okay, well, thank you very much, Rajesh, for that very, very kind introduction. I must say, I should also say a few words about the incredible work that you, Rajesh, and also Spenta Wadia have been doing in not only doing high quality physics in India, but also at the same time building this incredible institution, ICTS, which I love to visit, partly because it's in the town that I went to school in, Bangalore. And I hope the situation in Bangalore is going to improve soon, and I look forward to my next visit to see you all. Okay, so I'm really flattered to be asked this talk on big questions. That's not the way I approach my research normally. I just think about some tiny little question, and then maybe later on it has some impact on some other question. But so I started, thinking about how to phrase, how to present some of the things I've been working on in some big context. So I'm going to go really big, inspired by Rajesh. So forgive the reach, but anyway, I think it'd be fun anyway to connect this up to other big questions in the history of physics. So let me begin by Newton. So we've all heard of, in high school, learned the Newton's laws of motion. Well, they were probably not due to him. I think most of them are understood before what we learned in high school. But what was really new to Newton was something, also something more remarkable. What he showed for the first time, that the same laws of motion applied to the planets on planetary scales, which is about 1 trillion meters. That's roughly the size of the solar system. As they applied, to apples falling on Earth, that exactly the same laws. The laws were exactly the same. You could, by computing the motion of the planets, then deduce how fast an apple will fall. And this was really a very big thing, because it's really the first time that people understood that what's happening in the heavens is also what's happening on the Earth. It's the same laws. And so Newton, scanned a very vast distance scale from trillion meters to about a meter. And of course, and everything in between. And as far as people learned over the next 200 years, everything worked perfectly. So in some sense, Newton, as some people thought, that was the end of physics. What else is there to do? Of course, that's not true at all. And you could say the physics in the 20th century and the 21st century is about extending the reach of this range, go to even larger scales and smaller scales. And that's kind of what I'm going to try to do today, just quickly. So let's keep going to even smaller and smaller scales, from an apple to a dust particle to even smaller scales, grains of pollen. People could see that things worked exactly the same. Newton's laws were still okay. Up until around the early 1900s, when people started to understand that, in fact, Newton's didn't apply at a scale which is around 10 to the raised to the minus 10 meters, so it's 1/10 of a nanometer, which is the size of a hydrogen atom. So in a hydrogen atom, you have an electron in the Rutherford picture going around like a planet around the nucleus, which is positively charged, made of a proton. And initially, people started to apply Newton's laws of motion to this electron also, but it became very clear, especially from observations that I won't have time to go through, that this simply did not work. So there was just, again, a plethora of observations, starting with the so-called black body spectrum and various measures of spectra of atoms and so on and so forth. And then you would say there was a big event, almost as big as Newton's discovery of the universal law of gravitation, which was the discovery of the quantum theory by Schrödinger and Heisenberg in 1925. So there was a new theory which could describe perfectly, we know today, not just the structure of a single hydrogen atom, but hydrogen molecules, big molecules, DNA, and so on. So, and even big crystalline solids, as we'll talk about later. So, and this theory initially seemed like a small deviation, some correction to Newton's framework, but soon it became clear that it was something much more radical. It introduced a whole new idea into physics and into our theory of the universe that didn't exist at all in the Newtonian formulation. And this is the idea or the principle of superposition. So I'm sure most of you have heard about the famous cat, which is both dead and alive. That's, of course, just, nobody's ever achieved that. It'd be very, very difficult to have such a superposition of a live cat and a dead cat. But it just makes the basic point, which can be achieved in much smaller objects, is that you could have a physical system which is in two distinct states. For example, an electron, at one position and at a different position. You could make a state of the electron, which is, in fact, in both states at the same time. So you can superpose, you can take two distinct physical states and make another state, which is the sum or difference of them, or actually any linear combination. You can add and subtract states. So that's really when you dig down into what's going on in the quantum theory, it took a few years to appreciate this. That's really what's the heart of everything, the principle of superposition. So once people understood this, you can now ask the converse question. Now we've gone on to very small scales and you've discovered this principle. Now let's go back up and scale things up, not just up to a cat, all the way to the solar system and even beyond. Is this still apply? So the short answer, as far as we know today, the answer is yes. And I'll try to give you some flavor of the type of questions people have been addressing to go from the small to the large now. All right. So let's just take that one step at a time. So here I'm going to take two electrons, not one electron. So a very simple picture of a hydrogen atom is an electron that's orbiting around the atom, but it also spins on its own axis. And it turns out the spin is a very simple object quantum mechanically. So I quickly summarize by saying that the electron can only spin clockwise or anti-clockwise. So there's two possible states of the spin of the electron. Let's say the up arrow represents it spinning anti-clockwise, counterclockwise, and the left down arrow representing spinning clockwise. Okay, so now let's take two electrons, as you'll find in a hydrogen molecule with its two protons and two electrons. A very simple description of the state of every hydrogen molecule that's out there is this particular state. And this state is a superposition now again in the quantum principle of two physically distinct states. And the state on the left is an electron that's spinning, the first electron on the left atom is spinning, let's say, counterclockwise, and the electron on the right atom is spinning clockwise. But there is another distinct state where the electron on the left atom is spinning clockwise and the one on the right atom is spinning counterclockwise. So these are two distinct states. And in principle, if I could do a clever enough experiment, I could go in and measure which direction is this electron spinning. And I could either see a clockwise or a counterclockwise electron. But the actual state of the electron is the superposition of these two distinct states. It's really in both at the time. And until you look at it, you don't know which one it's in. It's really in both. Okay, so, but you do have something strange emerging here, which is the start of what we call entanglement. If you measure this electron and you find that it's up or counterclockwise, then the other one necessarily is clockwise. So there is a perfect correlation between their orientations, but you can't tell which one is up and which one is down, but you're sure that if one is up, the other is down. And it's only the act of measurement that determines which is which. All right, so that's, now the same idea of superposition already starting to sound very, very strange for a single molecule. But this is no question that this is what happens. So the word quantum entanglement is a modern word. I'm not sure exactly when it entered our lexicon, but this paper by Einstein, Podolsky, and Rosen, I don't think they used it in this paper either, but they really pointed out the essence and the mystery of entanglement. So one way to state their argument is, imagine you have this hydrogen molecule, and you do a very clever experiment where you separate the two atoms and their electrons without disturbing them, without disturbing the spin in particular. That's very hard to do, but imagine you could do it. In principle, you can do that. And this particular atom could be, with me in Boston in principle, and the other one could be in Bangalore. The quantum mechanics would say that they're still entangled, that they're still correlated. And no one knows whether the electron in Bangalore is up and the one in Boston is down, or vice versa. In fact, it's not even determined. It's only the act of measurement, which will, because of the way you perturb the system, this is kind of like the uncertainty principle in action, that will determine which is up and which is down. So it could be this way or that way, we don't know, they're still entangled. And it's only the measurement of one electron which determines the state of the other electron. So this is something that, in fact, EPR found unacceptable. I mean, they pretty much said in the title of the paper, something is wrong with quantum mechanics, or incomplete is the precise word they use. This can't possibly be the case. The theory is bizarre. And it seemed like something was traveling instantaneously from Boston to Bangalore. Okay, so the answer is this is in fact what happens. And nothing is traveling instantaneously. The concept we have to then accept is that the entanglement, or the concept of a quantum state, is not a local concept. And the state is not neither in Boston nor in Bangalore. It's really in both places. And that's really one of the radical ideas that comes out of quantum mechanics. Okay, So now today, of course, this was 1935, like this is an article in New York Times talking about an experiment not with 2 electrons, but with 2 photons, which are little lumps of light, 1.3 kilometers apart, where they did indeed say this does happen. And that I think now 5 years later, there's much even longer scales, much better experiments showing what people say spooky action, Einstein called spooky action, but again, that's apocryphal. I don't think he ever used those words, but anyway. All right, so that's then a description of entanglement of just 2 particles. Even in this experiment, we're talking about 2 particles on the very small scale. So let me now change gears completely and go big. Actually, strictly speaking, very, very heavy. We were talking about single electrons. Let's go to very, very heavy objects, black holes. So a black hole, it's so heavy that it's full of gravitation. It's so strong that if some atom inside the black hole emitted a beam of light, the light would start to escape the black hole, but then would be pulled back and would never be able to go off. So there's a horizon beyond which no light would ever escape from the inside of a black hole because the pull of gravity is so strong. Okay, and the existence of black holes and many of their properties really came about from Einstein's theory of general relativity, 1918, and that's before the invention of the quantum theory in 1925. It's an amazing theory, but one thing to keep in mind, it is not as radical a departure from Newton's equations as the quantum theory. It can be viewed as some kind of correction to Newton's equations when things move really fast near the velocity of light. It's really in the same Newtonian framework, except you have to, you have to think about curvature of space-time, but still within it's just an natural evolution of Newton. It's not a radical departure like the quantum theory was. So in particular, Einstein's theory would give you this radius of the horizon for a mass m, where g is Newton's constant and c is the velocity of light. This is the only equation I'm going to use. If you plug in here Earth's mass, you get a radius of 9 millimeters. So that's how dense you have to make things. You have to take the whole Earth and squeeze it down to 9 millimeters for the Earth to become a black hole. So this was thought to be completely ridiculous in the 1920s and 30s and much later. But today we know there's lots and lots of black holes out there. So now they're going really big. This is a picture that actually my wife, Usha, pointed out to me in the popular press recently, showing 25,000 what are called supermassive black holes. These are black holes that are 1 million to 1 billion times the mass of our sun. And each one of these dots represents a supermassive black hole at the center of its own galaxy. So we can't see the galaxy in this particular view because of the frequency at which they're looking at it. And each black hole is about 10 times larger than our sun, and is at the center of its own galaxy. In fact, it's almost as bright as the rest of the galaxy, and including our own galaxy as such a huge black hole at the center of it. All right, so now I've told you about the Newtonian Einstein theory of black holes and how they're out there, and everything in these and similar observations agrees with the predictions of Einstein's theory. But physicists being physicists, they don't stop with what's possible. They start what's been done. They try to think about what could be possible. So we developed this theory of the very small, the quantum theory. And so, like Newton, we're going to try to now scale it up all the way to black holes and ask, is there any effect of the quantum theory on black holes? Is it going to change anything? And this step was really first taken by Stephen Hawking, in a sense. That was his most important contribution. And one way to understand what he did, although he didn't phrase it in these terms, is to take a pair of entangled electrons and imagine that somehow you can separate them by putting one inside a black hole and the other outside a black hole. then the quantum theory would say that they're still entangled. There's no just because you're one is inside and outside the black hole, it doesn't matter as long as you didn't disturb the spin, they're still entangled, and vice versa. So that's again very bizarre. And one of the consequences of this was that black holes turn out. Okay, this I've already said. There's quantum entanglement between the inside and the outside of a black hole, and a consequence of this entanglement is that black holes are actually have a temperature. They're not just this quiescent body out of which nothing can ever escape. They're radiating very, very slowly at a very low temperature. Light and energy and small particles. And what Hawking computed, not by this argument, but as some related argument, that what the temperature of every black hole is, and we call it, of course, the Hawking temperature. But from the entanglement point of view, you can understand this in the following manner. Say I'm outside the black hole and I have this electron with me, it's entangled with the other electron, which is inside the black hole. But there's no possible way I can ever figure out over any conceivable time until the black hole totally evaporates, but we're not going to wait that long. What's happening to this one? So that that other electron is just totally gone. It's beyond the horizon. It's inside the horizon. So for me, this electron is really not entangled with anybody. It's totally random. And randomness, is the essence of temperature and entropy. That's how things become hot, and they become random. So this electron seems like a hot electron to me. And that's roughly how you can understand the existence of black hole entropy. All right, so this is one of the things, this is Hawking's really greatest discovery, that the quantum theory from the very, very small applied to the very, very big does have some consequences. Although in this case, the consequences so far are so weak that there hasn't been any experiment detecting this consequence, but who knows, in the future, there could well be. All right, so now I want to try to connect the small and the big with this entanglement a bit more. So Hawking had, of course, a very brilliant advance, but it was short of a complete theory. There's many questions. It opened up as many questions as it answered. You couldn't really tell, exactly how information was being preserved as the black holes started radiating away and evaporating, and what happened when it became really small. So there were many, many complicated questions the Hawking theory raised, which I think the community has made a lot of progress on, but it's still, I would say, there's still many, many open questions. Starting, even though there's been an enormous amount of work since Hawking's work. And part of the reason it's so difficult is that having a complete theory of a black hole or of entanglement on the scale of a black hole is that we have to consider not just two particle entanglement, as Einstein, Podolsky, and Rosen talked about, but multi-particle entanglement, an entanglement for essentially an infinite number of particles, all of the particles making up a black hole. We have to figure out some general theory of how they entangle with each other. And there's really no such complete theory. But this problem of multi-particle entanglement, however, in the last, I would say, 20 years or so, or 30 years, has started to appear in other branches of physics, which are closer to branches that I work on. Many of you may have heard about quantum computers, and in some ways, that is what quantum computing is. It's a way of controlling the entanglement of many particles. Computer scientists would call them qubits, in a way that you could compute something useful. But controlling entanglement is extremely hard because you have to really separate those degrees of freedom from everything around them, from the environment. And that's really, the challenge that the whole field is facing, whether they'll be able to overcome that. They're making small steps toward that direction, but I would say they're a long way from having some useful quantum computer at this point. And finally, another place where multi-particle entanglement appears is in the study of certain materials. Sometimes we call them quantum materials. These are crystals with multiple elements, which on their own display phases with multi-electron entanglement. You just make the crystal in the lab, and the electrons turn out to be entangled in some complicated way. And then you can study their properties. And this is usually the world that I live in. So here's a very famous example. It's made up of these elements, yttrium, barium, copper oxide. Here's a picture of little pieces of the crystal. Here's a structure of the various atoms that repeat themselves in this configuration to form a crystal like that. And it's what's called a high temperature superconductor. And what we mean by that is you could take this little pellet of yttrium, barium, copper oxide and dip it in liquid nitrogen. That's what's been done here to this pellet here, and it's placed over a bunch of magnets. And then, yes, I hope you can see the movie. There's this superconducting magnet floating over the ordinary magnets. And of course, it fell down because it got hot. Once it gets above about 100 Kelvin, then it no longer superconducts. All right, so this behavior was discovered around 1987, 1988, just when I was starting my career as a physicist. And I've been thinking about such materials ever since. They show what we call a phase diagram. This is here on the horizontal axis, you're changing the density of electrons in the crystal by some chemical means. Here you're raising the temperature. And here's the superconductor that I just showed you. But most interesting is some regime here that people call the strange metal. Strange, well, because it's strange. And our current understanding is this strange metal is actually a phase where there's complicated multi-particle entanglement really at essentially all scales in the crystal. And that's why the metal behaves in such a bizarre way. Okay, so that's the domain that I mentioned here earlier of quantum materials, where that's an actual material which displays phases in multi-electron entanglement. So there are black holes, there's quantum computers, maybe someday with controlled entanglement. Here we can't control it. It does what it wants to do, and we're trying to figure out what it's doing in the quantum materials. So let me just finish by mentioning the SYK model that Rajesh so kindly mentioned at the beginning. So this is a model that I cooked up in 1993, just trying to find some model of multi-particle entanglement from which you could say something definite. So it was really born of desperation. I was trying to understand the strange metal phase, and is still working on that. So we wanted to find some simplest model which you could make some progress. And it turns out we're still discovering many features of this SYK model. And it has some very interesting structure of entanglement, which is in a sense scale invariant, and allows you to go from the very small to the very big. So it has a scale invariant entanglement structure. Electrons entangled, really loosely speaking, at all distance and time scales. And understanding how that happens in this model has led to new insights on the physics of strange metals. And as Rajesh also mentioned, these days in understanding the structure of black holes. Okay, so what is the heart of this this ability for this simple model to describe such very different systems, apart from the fact that it involves entanglement? Well, if you, in the original variables that you wrote it down, it's very much motivated by what's happening in that crystal, how the electrons are moving around. We tried to make a model of how the electrons are moving around and got a strange metal. But over the years, inspired in particular by many developments in string theory, the concept of duality has played an important role. So you can take a new dual set of variables. So these are describing the same system, but in a very different way. And these dual set of variables, in fact, end up obeying equations which are very similar to the equations of Einstein's, the combination of Einstein's theory of general relativity and quantum mechanics. And this has led to insights on a certain class of black holes. Okay, so let me just, fortunately, it turns out I can describe the SYK model just in a few pictures. It's really that simple. And so I'll close with that. I'll show you a picture of it. So what you do is you take a bunch of positions and placed randomly. And then you occupy some fraction of them with electrons. So here, each purple dot represents an electron. I'm ignoring its spin, so it's just, just imagine the spins are all up. And you put a whole bunch of them on these traps. And now you want the electrons to move around, because of the uncertainty principle. They want to hop to other places just naturally from quantum mechanics. That's what you call tunneling from one side to the other. So the electrons, you want them to tunnel around. Now, if you just let them tunnel around as they wish, then you get a metal. So that's been understood for 50 years or even longer. If you take a bunch of random positions and allow electrons to move around, you get a metal, which is not what we want to understand. We understand metals extremely well. So what you have to do is just put a little twist, put a little restrictions on how they can move. And the restriction is that they move in pairs. That's it. So for example, this pair of electrons can tunnel from here, from these two sides to these two sides. Now the electrons are identical particles, so you can't distinguish quantum mechanically between this tunneling and this tunneling. It could be that this one went here and that one went there. They really both happen at the same time, effectively. And so you can see that what this process leads is an entanglement. It generates entanglement, even though initially it wasn't there. So these two can hop around. And that particular hopping happens at some rate, which depends on exactly the environment you push these electrons in, and so on. So you pick any two sites and you allow them to hop that way. And for each one of these processes, you attach a number. A number roughly tells you how often that particular event's going to happen when these two electrons move here to there. And in a real crystal, these processes happen, and it's a very complicated process to figure out what that number is that you attach to each process. So our idea, it's so ridiculous how simple it was to say, okay, I don't know what's happening. So to each of these processes, just attach a random number, an independent random number for every process. So everything that can happen is allowed to happen, and how often it happens is random. Amazingly, that gave really the first model that you could work out completely and understand now in great detail the structure of the many particle entanglement. Once you allowed each of these processes to have a random number associated with them. Okay, so they pair, and each of this entanglement is happening with a random amplitude, is the technical word that we use quantum mechanically. Okay, I think that's it. So that's what the SYK model is. It's really has entanglement at all distances in all times, and that allows it to describe things that are in a little crystal all the way up to black holes. And we're really learning a lot these days by connecting the very small to the very big, not only by the SYK model, but also many other models, including, and in particular, this duality that I mentioned is something Rajesh has made some very brilliant contributions recently, more in the context of string theory, the duality between these two different ways of looking at entanglement. So thank you, Rajesh.
Thanks a lot, Subir, for that, taking us through this vast landscape and giving us a glimpse of this. One of the things that I think most strikes me about these developments that you've been pioneering is the interconnectedness of ideas in theoretical physics, how you cannot really kind of put firewalls, so to say, between different areas. Ideas,
Right.
just, you have to let the ideas move around in idea space, and they find new homes, they find new remarkable ways, and each time you get these sort of when you view things, like when you start viewing black holes in terms of strange metals, that's just completely mind-blowing. I mean, that you can do that. I mean, they seem like completely poles apart, but that's, I think, the remarkable thing about physics. So please ask your
Should I?
question about. You can ask on the chat. You can unmute yourself, and or you can ask, put up your hand and ask to be unmuted, etc. Let's and feel free to ask about anything, as they say, that you were afraid to ask, anything about quantum mechanics that you were always that you were very mystified by. So as you can see, this structure of quantum entanglement is at the heart of a lot of things. I think even some of these new materials that Subir mentioned, these are things that are likely to sort of appear in our lifetime in things around us. I'm sure they are going to revolutionize technology in the future. So there's a question from Sandev about, is the duality also related to this Mulder-Sinner's duality conjecture from string theory?
Yes, of course. Yeah. So there's a duality in string theory, sometimes called the ADS-CFT duality, which is, I think, is much more than a conjecture today, especially due to some of the work by Rajesh recently. It's essentially proven that there's a duality between, well, what are called conformal field theories. So conformal field theories are not quite strange metals. They're similar, but it's another form of matter that's doesn't occur in the real world, in the natural world, that easily, with long range entanglement. So that's a duality between conformal field theory and black holes. The duality between the SYK model and black holes is a cousin of that. It doesn't have a conformal field theory on one side, of exactly the same type, and yeah, okay. And it's in fact a much simpler version of it, because it's essentially proven without any doubt by starting from either side. Yeah, okay. But the two are similar.
So Raja,
but I will say that although I was able to describe the SYK model in a few pictures, you'll have to take a whole year of string theory to understand conformal field theories. So it is a lot simpler.
So Raja Banerjee asks, how do two electrons decide to entangle, in some sense? Or when
Yeah.
how do they get entangled? Or yeah.
Right. So I think so. These pictures that I showed were kind of misleading. So let me share again. I mean, that's the best we can do, right? So so you have these electrons, and I was sort of pretending that things are evolving in time, that these electrons sit here, and then two of them move, and then the two of the others move, and so on. But really, they're all happening at the same time. So the time evolution in this slides is totally fake. There's a certain amplitude for any pair of electrons to entangle. So it's a number that you assign at some point, but depends on how far apart they are, what's the nature of the interaction between them. There's some electrical forces that you have to worry about. So once you know all those forces, there's a certain rate at which they're going to entangle. And that's true for any pair of electrons in the set. And what makes this quantum problem is all of that's happening at the same time. It's not as if these two are entangled and the other two are entangling. That's really a Newtonian point of view, if you wish. If that was the problem, we could solve it very easily. You could just write down some kind of Markov chain and just write down some probability distribution of the electrons. That is not what happens. They're really all entangling together at the same time. That's what makes multi-particle entanglement really complicated. I hope I answered that question.
It's Shashi Upadhyay. By the way, I should mention to you, Subir, Shashi, Senthil, and I were all classmates in the same year in physics. Senthil, for many of the IITK people on this call, did his PhD with Subir. So connection.
Yeah, well, that was a very distinguished IITK class, yes.
Shashi asks, why is it so hard to achieve artificial entanglement in quantum computers while easy to find it in natural systems like high TC materials?
Well, it's because entanglement is always hard to achieve if you want to achieve a certain type of entanglement. So in the high TC materials, they achieve some sort of entanglement, which depends on all kinds of details of their structure. And we're just trying to figure it out. We're trying to measure what's there. If you wanted to change it and control it to something that we want, that's extremely hard. And that's really what we want to do in a quantum computer. You're not just studying the entanglement that happens to be there. You want to make your own entanglement in a way that does something useful for you, in the sense of computing something. And to do that, you really have to take each electron and control its entanglement very precisely. And so, people have all kinds of ingenious ideas on how to do that. Almost certainly you're going to make errors, so you have to have quantum error correction. And the current status of things is that even for a single electron, no one's ever made a fully, what's called a fault-tolerant bit that you could, that could correct its own entanglement by some error correction method. So that's a very, very challenging problem, but well, okay, people have all kinds of creative ideas on how will move forward. I mean, my own view is that, it's sort of like going to the moon. It's a very nice goal to have, people's colonies on the moon or something like that. But along the way, we're going to discover all kinds of amazing things and useful things. And I'm sure that's what's going to happen with quantum computers. Nobody knows what they're actually going to be useful for. I doubt they're going to be useful for, factorizing big numbers, which is sort of like going to the moon. But there could be many other things, or going to Mars, I should say. Yeah. Okay, that's a personal point of view. Many of my closest friends in my department disagree with me, but okay. Rajesh, you're muted.
Sorry. On the subject of entanglement, Ashok Vaish says, you've piqued our curiosity. Do you have an explanation of what resolves an entangled state? Meaning, what's an observation that causes the cat to choose whether it's alive or dead? I guess the wave function collapse. Is that still the mysterious issue that it?
Well, I mean, so the cat, it depends what you mean by the cat. The cat itself, just the air molecules that the cat is breathing. As the cat breathes the air molecules, those air molecules are entangling with the cat. So that, in a sense, will break. So if you try to make a superposition of a live and a dead cat, you have to get rid of all the air, and that will kill the cat anyway. So you really have to totally isolate it. And so that's just a picture that people like to make. I think people have made what they call cat states of maybe 100 electrons in a very controlled environment, in a in a very cold system where there's essentially no air, nothing. It's an ultra high vacuum, and under certain conditions, then you can make cat states, of say 100 electrons, where all electrons are up and the dead cat is all electrons are down. So that's what people call a cat state. But I still wanted to show the picture because then everybody knows what I'm trying to say.
Yeah, but I guess the question of the collapse of the wave function is still whatever it was 100 years ago, right? I mean, that's not something we have even.
Well, I would say, I think one view is that the collapse of the wave function itself is entanglement. So when I look at something,
yes,
my brain, I have been entangled with what I'm looking at. And since I'm entangled with what I'm looking at, I'm going to see what I'm entangled with, which is one of the states. Right. But this raises the philosophical question, what about the other me, which saw the other part of the state? Well, I don't know what to do about that, because that's not something that I'm observing.
Yeah, that gets us into many worlds and so on.
Right.
By the way, there's a very interesting graphic comic I was recommending to Subir's wife last time we met. I think it's called Totally Random, and it's by, I think, Jeffrey Bubb and I think his wife, who was the illustrator. But it's a graphic novel. You can find it on Amazon, and it explores many of these ideas in a very fun way, meant for non-technical audience. So Vineet Gupta asks, quantum entanglement can be used to teleport particles. Is this something that can be used to transmit information across long distances? I guess it's not more about, quantum.
Yes, I think that's correct. So you can do quantum teleportation. You're not teleporting actual matter. But the second part of your question is the correct way to say it. You're really sending quantum information. So if you have a quantum state here, if I have an electron sitting here, and it's in some superposition state, it's both up and down. And I don't know exactly what kind of state it's in. And if I look at it, I will see it either up or down, and I'll have destroyed the state just by the act of looking at it. But what I can do by a very clever protocol, without that, I can take my electron in a certain state, and it's important that I don't know what state it's in. I can still send it from here to Bangalore in principle, so that the person in Bangalore has the same state. The electron in Bangalore has the same state that I have here. No electron has moved. I can send the information by a beam of light or something. Well, actually, not even a beam of light. What it requires is that you take this pair, this EPR pair that I showed you, and so I have to go to Bangalore. We have to create an EPR pair. Then I have to come back to Boston carrying my half of EPR pair, and the person in Bangalore, Rajesh, has the other half. So we met for a while. We shared this EPR pair, and then I can bring in another electron over here and send the information on this electron without knowing exactly what state's in it, all the way to Bangalore. And I can be confident that Rajesh then has the same state that I had before in his electron over there. That's what teleportation is about. It's not magic. You have to have some contact in the past where you share entanglement. And then you can use that in the future to send quantum information.
Yeah, that's why it doesn't violate relativity, as Vineet was wondering. Yeah. So Anand Rajaraman asks, once a pair of electrons are entangled, do they remain entangled forever? Or is there a probability that they disentangle?
Great question. Yes, they can disentangle. I mean, you have to bring in some other electrons, and with the right sort of interaction, you could disentangle them and transfer the entanglement to the other one. Quantum teleportation does something like that.
Yeah. This from YouTube, there's a question by Pierre-Luc. Are different strange metal states always distinguishable by scattering experiments?
Well, that's a great question. I think I would say we're still in the process of classifying the different possibilities for strange metals. There are many different materials that show strange metals. They are similar and different to each other, but some of the details are different. The temperature range over which they exist and their response to various spectral probes is different. And there are theories for many of them, although that's still a subject of active research. And those are also, the theories are similar to each other and similar in some ways to the SYK model also. But we still don't have a full, I would say a definitive classification of strange metals and the full taxonomy of these are the 5 different kinds, and this is what you'll find in this material and that you'll find in the other material. My hope is to reach that maybe someday. That's been a goal of my research for a while.
So there's a question, there's a question probably that needs maybe some clarification. What force is involved in quantum entanglement? I guess there's no real force. But
yeah. I mean, I would say it's sort of like, let's go back to Newton's laws. So Newton's laws have kind of 2 components. One is force equals mass times acceleration. And the other is that the force of gravity is, G m1 m2 over r squared. So the force is gravity, what we call the kinematic part, which is F equals ma. It applies to any force. F equals ma would apply to gravitational forces, electrical forces, in principle, also the strong and weak forces, if you could find them in the right regime. So there's the actual force of many different forces, and in the strange metals that I deal with, it's mostly almost all electrical forces. But then there's the kinematic part, which tells you how does the position and momentum of the particle respond to a certain force. And that's what quantum mechanics tells us. It's independent of what particular force you're using. It's a statement of the evolution of the quantum state for any force. And what was the precise question? I think I may have forgotten. I think I answered the question.
I think that's a sort of a general question from Ken Hertz. Do you find yourself making connections or drawing analogy between phenomena in physics with other areas of life, such as philosophy, art, or human behavior?
A great question. Yeah, I try to avoid that. I think I think I leave the philosophy to the philosophers, and you could say we have very narrow points of view. I mean, there are people who make connections between the duality and the concepts of duality in religion and philosophy. There may be, I know, at some level, but that it's hard to phrase the connection in scientific terms, which will actually influence some of the things I'm thinking about in my work. Yeah, I mean, I guess what I would say is that the reality of quantum theory, if you want a more philosophical point of view, is so, and of these black holes, the supermassive black holes, the galaxies, and the electrons, and it's so incredible and so unbelievable that even the most fantastic stories of origin in religion don't come to the actual close to the truth. It's much more fantastic than anybody, even humans, ever imagined. And so all stories of creation are just a weak imitation of the actual reality. Okay, that's as religious I'm going to get.
But I mean, narrowing things a bit across different areas of physics, I mean, how do you find yourself sort of thinking about something like black holes, which was so far away from your original interest? How do you find yourself thinking about making these connections, or is that sort of organic, or is it something you kind of when you're hearing talks from other areas, do you try to make the connections there?
Yeah, no, I mean, I guess thinking back to my own progress on some of these topics, I mean, in almost all cases, I've been just focused on what seems like a very narrow question. But we try to really understand it well and not accept the easy answer and, write a paper and then move on to something else. You really want to dive into the depth of it and start trying to make progress. And then, and while you're working this question, you kind of be open to what else is going on. Go to lots of seminars in different fields and just being listening. And then, go to conferences, talking to people, and then every now and then, suddenly somebody will say something that will make a connection. That's typically the way it's happened for me. It's not that I'm sitting in my chair and trying to think the big thoughts. Usually, you're trying to think the little thoughts, and hopefully some connection gets made someday.
So Anand Rajaraman asks, what is your prediction for how long before we see the first practical applications of quantum computing? Will it be in our lifetimes?
I would say, define practical. I would say within, okay, all right, I have a lot of friends in this field, and no matter what I say, they get upset at me. But I'll go out and say what I want. I would say in our lifetime, maybe, we'll understand more about the structure of matter and structure of complicated quantum mechanics in the kind of materials I was telling you about, or more complicated molecules that are important in chemical reactions. So there's a, ordinary computers, classical computers, I find it very, very difficult to factorize large numbers. And that's one of the problems that we hope quantum computers will solve. But there are other problems that are very, very difficult for ordinary computers. And this is like computing quantum mechanics, computing the effects of quantum entanglement on physical properties of a certain crystal or of a certain big molecule. We can't compute it very accurately by an ordinary computer because it's just impossibly hard for reasons I won't go into. But quantum computers can simulate some of this. And I think so these quantum simulation tasks, as they're called, that's looking very reachable in the near term. In the near term, meaning, in the lifetime I have left as a researcher. I think there will be real progress there. And there's already quite a bit of exciting work in that direction, even in the last few months. And will that have some practical impact? Well, it's hard to tell. I think eventually it will. I mean, if you go back and look at, of course, the big story we always like to tell, the development of the transistor and the laser and how it launched the electronic revolution, that all came from advances in quantum physics and understanding the quantum behavior of electrons in materials. And I think there's very likely another frontier in that direction that could well open up. So I wouldn't worry about, RSA being suddenly not safe. I'm not worried about that in my lifetime. But I think there could be many other benefits from quantum computing.
I mean, there are many different kinds of approaches people take to building quantum computers using superconducting qubits, or maybe even then there are the ideas of using topologically protected states. So do you think that some of the, in some sense, progress in understanding, so do you think like these topologically protected states, they seem attractive on paper, that you are kind of protecting that entanglement that you talked about in some very rigid topology? Do you think something like that could eventually materialize. I think so far people are struggling, if I'm not mistaken, to realize something like that.
Yeah. So my my own view is that the topological way of doing things is really the only way that will eventually succeed, if at all. I mean, I think the people trying topology, which is the Microsoft group, they seem to be much farther behind right now from, say, Google or Intel or any of the other people using other methods. But the other methods, they really are what I would say is doing quantum computer science rather than quantum physics. They're trying to take ideas from computer science and how you correct errors and implementing them in a series of gate operations. And once you have a whole bunch of sequences of gate operations, I'm skeptical that the quantum computer science model of the real world is actually going to work once you get a very large number of bits. Okay, that's a minority point of view, I should say, but that's my opinion. There are a few friends of mine who would agree with me, I think, I would say. But the topological way of doing things, in some ways, what they're doing, one way of saying it is they're putting the quantum error correction right in the hardware. It's a hardware level quantum error correction rather than a software level hardware error correction. So they're really actually carefully studying the entanglement of what actually makes a bit, rather than taking some gate model that may not reflect reality. What actually makes a bit, they have a theory of what makes a bit, and then from that theory and their understanding of it, you can argue under very general conditions that there should be quantum error correction possible. And I mean, those arguments I find very persuasive. But on the other hand, implementing error correction at the hardware level is extremely difficult, and Microsoft has a huge effort trying to do that. We still haven't, as I said, no one's fully quantum error corrected even a single bit. But I would say once that's achieved by Microsoft or whoever does it, then the road to building an actual quantum computer is far easier in the topological direction. That's my view.
Yeah, just for me also, just as a total outsider, that seemed like the robust way to sort of go about it.
Yes.
But I always got the feeling that it's a bit of the underdog right now. But yeah, but usually it's the underdog that.
Yeah. But you know, with the superconducting qubits and the ion traps, you can make a few qubits and have them do fun things, and it looks great. And now they've gone up to 50 bits, but they're very quickly, they're not doing computing. What they're doing is quantum simulation. Really, that's what they're all doing right now. And okay, I don't like to say I told you so, but I told you so.
So JP Jaina wants to know the distance across which quantum entangled phenomena can be realized. For instance, the activities on Earth can be controlled from a distant galaxy, I guess, in some science fiction-ish the same. But I guess the science question is are there limits to the distances across which quantum entanglement can be realized?
No, as far as we know, there aren't. I mean, you can have particles on two sides of a black hole or even two sides of a galaxy be entangled with each other in principle. But about somebody from a different galaxy controlling us, there is, unless we interacted with that galaxy at some time deep dark in the past and shared some mutual entanglement, and that entanglement didn't get destroyed by other perturbations, there's no way for them to control us. I mean, it's not some, like Star Trek quantum teleportation from here to there. There has to have been some interaction in the past, which was coherently preserved until today, for quantum entanglement to be useful for something like quantum teleportation.
I think there's one science fiction novel I read which sort of tries to take this. It tries to bring it in a little more scientifically like this. I think by creating that initial contact, and then having this other galaxy kind of try to control things on Earth. It's by the Chinese science fiction writer Cixin Liu, I think, the three-body problem. And its sequels, but anyhow, that's, I think, science fiction. There's another question from Pierre-Luc, which says, are there not already consequences of having gone from a classical to a quantum formulation of information theory? So presumably meaning just that, yeah, the rules are very different for quantum information and the limits of quantum information. So are there consequences in for leaving aside quantum computing, I guess, in the transmission of information?
Sorry, I missed that. Excuse me. Yeah, are there limits to it?
I think it's, are there, the question is, are there not already consequences of having gone from a classical to a quantum formulation of information theory? I mean, is that, I think that's, if I can sort of read between the lines, it's, are there drastic consequences? Are there radical sort of changes in doing that?
Well, I mean, the classical information theory of Shannon is pretty much still valid, and I think the flow has been more the other way, people taking ideas from classical information theory and helping understand quantum entanglement using information theory. And so there's been a huge explosion of work in using quantum information, not just for transmission of information, but also for even asking questions like what happens when a black hole evaporates. So the kind of thought, suppose you had a black hole and it started radiating like Hawking said, and eventually started evaporated. And then I gave you a different black hole, which only differed by somebody threw one particle into it. So these are almost identical black holes, but their initial state is slightly different. Could you, by looking at what's coming out, the information that's coming out from the radiation, tell which black hole had that extra particle thrown in? So that's one of the deep questions that string theorists and others have been sorting out these days. And the answer is yes, you can, but it's extremely difficult. But at least in principle, you can. And I think ideas from classical information theory have really played an important role in understanding questions of this type. I mean, correct me if I'm wrong, Rajesh. Rajesh knows more about this than I do.
Perfectly on the nose. So Vibha has a very interesting question. Does the Big Bang imply that everything was entangled in the past? And of course, she says, she, as a non-scientist, it's a sort of a general question on her part, but I think it's an interesting question that.
Yeah. I mean, there's questions of inflation, right? So if you didn't have inflation, then people were not causally connected at some point. I think there's still, I believe, there's the visible universe, which is the time it takes for light to travel from the Big Bang. You take the time from now to the Big Bang, which is 13.6 billion years, and you go out 13.6 billion years in space, you still, that's our visible universe. It could, who knows what's beyond that? And in principle, I think we could be entangled with anything in the visible universe. Yes.
Yeah, I mean, I guess there's a question of, like you said earlier about Newton's laws, there's the time evolution, but then there's the initial state. And we still are, I mean, there are hypotheses of what the initial state was. I mean, there are some natural initial states you could consider, the so-called Bunch-Davies vacuum and all the for inflation, which would mean that there, and as Subir said, there's a horizon due to the inflation. So things in some sense, just like the black hole horizon, are sort of entangled across that horizon and us as well. So there is a certain sense, and there's a certain sense in which the space-time inflationary space-time has a temperature, like the black hole has a temperature. So in some ways, yeah, but we still don't know whether that's really the case or not. I mean, these are these are just ideas about what the initial vacuum was like, and we still don't have a theory which tells us this thing. So yeah, but it's a very valid, very interesting question. Ashok Vaish asks, I wonder if there's a radical impact on causality due to quantum mechanics. We still seem to cling to the view that the cosmos is deterministic in principle, given sufficient computational ability.
That's a very good question. So the equations of quantum mechanics are deterministic, despite the uncertainty principle, in the sense that, and there's no violation of causality, in the sense that if you knew the quantum state at time t equals 0, then the equations of quantum mechanics, in principle, fully determine the quantum state in the future. Where, in a sense, the uncertainty comes in is that it's impossible to know the quantum state. If I give you a little electron in a box and tell you, here's your electron, and I tell you, predict its future, well, your first choice would be, well, oh, let me look at the electron to figure out its state right now, and then I'll predict the future. But just by the act of looking at it, you will destroy the electron. On the other hand, if I gave you an electron, I told you, it's in this state, I just tell you, it's in this state. Then knowing that, you can predict the future of the electron. But you have to believe me that I told you the truth. There's no way of confirming I told you the truth. Okay, so that's a very simple way of putting it. Equations are deterministic, but it's, there's a certain unknowable aspect of quantum theory that you can't fully determine an unknown state. That's where the uncertainty comes in a sense. But causality and determinism are really not, are still present. It's just harder to implement them.
So let me just I think we should close very soon. It's quite late for people.
In fact, I have to go get my second vaccine in an hour.
No, but, yes. So we just close. I just wanted a last distinct thought from you, Subir, about you mentioned in the last 30 years or so, 20, 30 years is when the idea of quantum entanglement in the understanding of various phases of matter and materials has really kind of come center stage. So do you see radical new developments in kind of producing new materials, or kind of seeing amazing new phenomena coming over the horizon? Is it something that you feel is, I mean,
well, if I knew what was coming on the horizon, I'd be working on it. Okay, I would no. So it's hard to predict, but you can look at the recent past and see all the sequence of incredible discoveries, and they don't seem to be, slowing down in any way. Just in the past couple of years, it was twisted bilayer graphene. There's different compounds showing spin liquid behavior, or quite, and then now. Very recently, I've been involved in some work by Misha Lukin's group at Harvard on realizing a spin liquid using cold atoms and lasers. I think Shubro actually at ICTS played an important role in that. I think there's, I would agree with you that there's a lot happening on the quantum frontier in physics, all the way from materials in the lab to new understanding of, very deep understanding of quantum information near black holes. And amazing thing is that they are connected in some way.
I get the sense that it's like the tip of an iceberg that one is sort of uncovering. And so, of course, much of the iceberg remains hidden, but hopefully it's going to come into view in the coming years, and it's probably an exciting time for young people to be getting into the field, asking questions about this. So we'll just take last question from Raja Banerjee about what happens to the entangled electron when we observe the state of its pair. So presumably
yeah, so that's it will change. That's really what EPR were objecting to, that if I have a pair of entangled electrons and one is with Rajesh and one is with me, if Rajesh looks at his electron, then my electron will change to a particular state that's determined by the consequences of Rajesh's. I shouldn't say determined by, that's connected to or correlated to the consequences of Rajesh, not the consequence, connected to what Rajesh observed. But for me to actually make sure that the entanglement was correct, I would have to call up Rajesh and say, what did you observe? And then Rajesh would tell me what he observed. And then I would see that was consistent. So that it does, and that information only travels at the velocity of light or slower. So that's when information gets transmitted. So what you can do with entanglement is not, you can't send information faster or instantaneously, but you can send it securely. So for example, I mean, this is there are better algorithms for this, but suppose I know that Rajesh and I are entangled. I have a pair of electrons that's entangled, so that when mine is up and his is down and vice versa. So then we share this in the past, and then Rajesh looks at his electron and it's down, and I look at my electron and it's up. So at this point, I know that Rajesh's electron is down, and no one else knows this. So I can call up Rajesh and say, if your electron was down, invest in this company. If your electron was up, invest in the other company. And no one can tell what I told Rajesh, even if they heard what I told him. But Rajesh will perfectly understand what I said because we share this information. So that's the way you have, that's the very simple explanation of quantum cryptography. You can securely send information, but that's not any faster. Okay. You're muted, Rajesh.
Sorry. So thanks a lot, Subir, for very patiently taking so many questions, spending time with us at such a moment. I mean, I hope you get your second shot very soon. And
I have plenty of time. Yeah, right. You've got your second shot already, I hope.
No, I'm still, yeah.
Oh, really?
I mean, I've got my first shot about 4 weeks ago, so I'll hopefully soon get it. There are issues, there are shortages here, but let's see how it goes. But anyway, everyone on the call, please stay safe. All the best for you and your families and friends and everyone. It's a difficult time, but anyway, I hope you got a little respite from that this thing here in this marvelous world of quantum mechanics and entanglement. So good night, good day, and so on to all, and bye-bye, Subir. And
thank you, Rajesh.
Hopefully soon in India when hopefully things get better.
Thank you.
All right, bye-bye.
Thanks.